All right, so we are going to re-look at some of the stuff from grade 12, and our first topic that we're going to look at is relations and functions. And so in your notes, you have some places that are boxes so that you can pay attention and like, ooh, I get to write down a word, and it's super fun. So domain and range of the functions are very important. What are your x values and what are your y values? So what is a relation? That's a situation where one thing is linked to another thing. We have functions and relations, and we deal with a lot of them in math, but you could also just say some sort of like, how's your mark in the course compared to how much you like a course? Do you usually get higher marks in courses that you like and lower marks in courses that you don't like? Is that probably a thing? And sometimes you might get a high mark in a course you don't like, or in a low mark in a course you like. Could happen, but there's a relationship between them. So the domain, those are your x values, and the range, those are your y values. So you can have a relation shown in a bunch of different ways. Probably most common that we're used to is like an equation or a graph, but you can have a relationship as a set of ordered pairs. You could have a relationship as a table of values, points on a graph. This is a mapping, so this is your x values and your y values. 2 goes to 0. In this one, 1 goes to 0 and 1 also goes to 5. And we would say that some of these are also functions, but some of them aren't functions. I don't know if you remember things like a vertical line test or the definition of a function. If something's a function, every x value can have only one y value. So that's why the vertical line test at, like right here on my y-axis, if I draw a vertical line, I hit 2 points. So this would not be a function because the x value of 0 has 2 different y values. And we don't like that as far as mathematical things go. You want your calculator to function. You don't want to go 2 plus 2 and sometimes it says 4, but every once in a while it's like, I'm going to go 8 this time. Like, what the heck? Shouldn't I always get the same answer if I do something? Then it's functioning. But there are sometimes some things in real life can't be functions. Right? Just based on how tall you are, I can't decide what pair of pants I'm going to buy you. I'm not going to buy you guys pants. But if I did buy you guys pants, there's different sizes of waists. You can't just say people that are this tall all get this size pants because of the length. There's also another variable, the waist, right? So their height and pant size is a relation, but not a function. Because you have to get different waist sizes involved in there. So we can't always tell, right? Can you imagine your age and your math mark? Just turned 16, my math mark just changed to 80. Yes. No, it doesn't work that way. There's a lot of 16-year-olds with different math marks. So this last one, wouldn't be a function either because the number 1 goes to 0 and it also goes to 5. So a function is a special kind of relation where every input, every x value has a unique output. You still can have the same y value, but every x value can have only one y value. So each element in the domain is assigned exactly one element of the range. So this would still be, if I have this, 1, 2, 3, and this as 0, right? This is the function of how much money you give your teacher and how many bonus marks he'll give you. So you can give me $1, and I'll give you no bonus. You can give me $2, and I'll give you no bonus marks. You can give me $3, I'll give you no bonus marks. So that function is, it's still a function because each x value has one y value, even though it's the same y value. So functions are a subset of relations, and that's what this circle is showing here. That every function is also a relation, but not every relation is a function. So we call the x value the independent variable and the y value the dependent variable. Talked about this a little bit earlier. We can tell from a graph if something is a function or not, based on something called a vertical line test. And the way the vertical line test works is you draw a vertical line. There we go. And once you have that vertical line drawn, and you can have it drawn in your head or you can use a ruler, you go from left to right on your graph. And you ask yourself, at any point as I'm going from left to right, do I hit the graph more than once? Because what the vertical line is representing is a unique x value. Here the x value is 0. Is there only one point that it hits? Yes. Then at that point, it's a function. But in order for the whole thing to be a function, you have to go from left to right and never hit more than once. So this first one, would it be a function? Yes. Because no matter where I draw this vertical line, I never hit more than one point. However, this second one is problematic in a bunch of places. It only has to be problematic once for it not to be a function. Like I can say, this is my graph, and it also includes this point. We just destroyed the function. Now that graph is not a function because there's one place where my vertical line hits two things. I'm going to erase that dot so it stays a function. This one is not functioning in a lot of places. This is a relationship. Anybody know the mathematical name of that shape? Oval is a good word. It's not the math. It's a mathematical word. Describes the shape, but its official name is an ellipse.
Oh yeah, right.
An ellipse is one of the famous four conic sections. If you have a cone, which I happen to, right here. The yellow one right there is the ellipse. Anytime you cut a cone on an angle, you will not get a circle, but you will always get something that is perfectly an ellipse. If you cut the cone perfectly flat and drop it a couple times, you will get a circle with some chips. If you cut a cone perfectly on the same angle as the side, that pink one, you've studied that shape before, that's your parabola. And different parabolas will be made at different places that you cut on your cone. And if you cut your cone perfectly straight up and down, you will get a hyperbola. You only study circles, parabolas. We might have a few ellipses in some of our questions. But those are the four conic sections. So this ellipse is not a function. And then we get into the little details. Like this one seems to be a function. Everything's going good here. This looks weird. Then it seems to be good again there. So we have to decide at that weird section right there, is this a function or is this not a function? And it is a function. The weird part there, the dot that's solid is included, The dot that's open is not included. So this graph has what's called a jump discontinuity, because it's not, you can't just continue along the way, you have to jump from this point down to there to keep going. And it is still a function, because at this value, which looks like, I don't know, we'll pretend it's 7. At 7, the value's up here, but not down there. So this is a function. So we can tell from a graph, using the vertical line test, if it's a function. If it also passes a horizontal line test, which none of these do, if it passes a horizontal line test, that tells you the inverse is also a function. And it has a special name. Those that pass both line tests, we call one-to-one functions. Because there's one x to one y, but there's also one y to one x. Function notation, we write f of x. You've seen that before. That's sort of the same idea as y. Sometimes you have an equation that's y equals. Sometimes you write f of x equals. The f of x is the function notation. The x is your input. And f of x as a whole thing is your output, or your dependent variable. So what's nice about function notation is that your dependent variable tells you also what your independent variable is. Height is a function of time. That'd be very weird if trees didn't grow that way. They just randomly had different heights at different times. You like plant it one year, next year it's a full-grown tree, then the year after that it shrinks down again. That would hurt our brains if we messed up some functions, just made them more random. I think it would really be weird. So, let's do some math. Given f of x is that equation, it's a parabola, you have to figure out f of negative 2. Try this one on your own. See what you come up with. You can try the next couple of them. You can keep working, but you can double check. Did you get 23 for the first one? Some things to be careful on, especially with negative numbers. When you plug it in, if you're showing your work, make sure you plug in the negative 2 in brackets. Because otherwise you might get confused and think -5, -2. Common mistakes way back in grade 9 and grade 10. Probably if you've made it through grade 12 pre-calculus, you're not making those mistakes as much anymore. But being careful with our notation is important. And then you can do order of operations and get 23. So just wanted you to see that, make sure you're on the right track. Is that the next one? I start putting the letters in there? I went from really easy to like more complicated pretty quickly. Same idea, wherever there's an x, right? When you had the -2, you replaced every x with the -2. So if you have an x plus h, you would replace every x with an x plus h. Right? I could even do a function where I put a person in there. Right? I could do f of Nikita. And then it would be Nikita squared. I don't know what that would look like. It might be kind of scary. But you could, whatever, it's a function, whatever you put in replaces the x. So this is step number 1. F of x plus h gets squared minus 5 times f times x plus h. And then we would have to do order of operations. So you would square the x plus h. And then multiply out. And you get this big, crazy thing. 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 1. And then in part C, we take what we did in part B and we subtract f of x. So in part B, we figured out all of this. And then we want to subtract all of this. This is where we're going to be careful as well. When you're subtracting something, you're subtracting all of it. So I need to make sure that that's in brackets when I subtract it. And then if you combine your like terms, all the 3x squared cancels out, the 5x cancels out, plus 1 cancels out. And you could write it like that, or you could write it factor. So we could factor out the h. Now this f of x plus h minus f of x is actually quite famous. It's actually like a building block of calculus. This is the starting of doing derivatives. But we have to know how to do the function notation first. And we'll find out why we would want to do this later on. But I accidentally made you do some calculus in the review. I'm sorry. We're advancing too quick. Don't worry. It's going to be all good. But the key idea is in function notation, what does it mean? Whatever you're plugging in, just like in this last one, whatever I plug into the function, that replaces the x. And then you just have some algebra to do afterwards to figure that out. We're going to figure out that this is really helpful for calculus. But that will come in a bit. And this part in calculus is called the difference quotient. And the difference quotient is that function, f of x plus h, minus f of x, but then it gets divided by h. So in the last question, we did just the f of x plus h minus f of x. When we factored out that h, and dividing by h's, those would cancel out. And that would show us exactly what the difference quotient is. So I'd like you to do some math and figure out the difference quotient for each of these. So you're going to have to figure out the f of x plus h, then subtract the f of x, and then divide by h. And again, I'll put the answers up in a little bit. I'll put up the answer for the first one. Did you get that f of x plus h was 3x plus 3h minus 1? And then if you subtracted, so I can write that in here, and then subtract the original, which I have in brackets, I have a bunch of like terms. The 3x minus the 3x will go away. The minus 1 minus the minus 1 will also go away, and I just get 3h over h, which simplifies to 3. And when we do our calculus unit, you are going to find out that the derivative of f of x equals 3x plus 1 is 3. The answer, somewhat of the answer to the difference quotient, is something called the derivative. So there's the answer to the first one. You can try the next two. And you'll find often in class, I'll get you to try things first, because that makes your brain work. And then we'll go over the answer and ask questions after. Put the answer up for B. So you can see, did you get there? Negative 2x minus h plus 2. Now I'll put the rest of the stuff up to see if you didn't get there, maybe where you went, something went awry. So plugging in x plus h, again I put it in brackets, I do my order of operations would be squaring first and then my negative and simplifying. Now I need to simplify in this question to get the answer, but you know how you might have been a little bit excited in grade 12 pre-calculus when I said, hey, you no longer have to simplify fractions. Right? You could leave your answer as 12 over 10. You no longer had to rationalize the denominator. You could leave a square root on the bottom. Those are things in grade 12. It's actually really hard to do, but in AP Calculus, you no longer have to do any arithmetic. In other words, if they asked you for what's f of x plus h and you left your answer as line number 1 without simplifying at all, they'd be like, perfect, no problem. If you wanted to leave, instead of leaving your answer as 1, You could leave it as 10 minus 9, plus 7 minus 7, plus 3 minus 3, plus 2 minus 2. If you wanted to. I'm not going to recommend that, because I'm sure that someone marking would be like, get frustrated with you and be like, ugh. But you don't have to do arithmetic in AP Calculus if you don't want to. You can leave your answer as a big. But usually, you want to simplify it on your own. That being said, Mr. LaFrance and I like you to do arithmetic. So on all the labs, we will expect you to get a final answer and simplify it. But on the exam, if you left something as 3 plus 5, they'd be like, that's okay. And then we do the difference quotient here. Here's my f of x plus h minus my f of x, all divided by h. And you might notice that, right, this negative would get distributed, right? And that minus x squared will cancel out with the plus x squared. And this 2x will cancel out with the minus 2x. And we're left with just the 2xh, the minus h squared, and the plus 2h, which you could factor in h out of. Really nice, because if it's multiplying, then you can simplify those. And just get negative 2x minus h plus 2. And the last one has something interesting happening to it. First of all, if you got this far, that's as far as I thought you would get. And then did you say, that's all I can do? Most likely. But there's something you can do with square roots that's interesting. And you've done this a little bit before in grade 11 when you had to rationalize the denominator. So I'm going to, first of all, go back to something in grade 11, which I'm going to guess most of you have forgotten. But what I'm going to do as a starting point is say, do you remember in grade 11 that you might have had something like this? And it wasn't allowed because you had square roots on the bottom. Do you remember how to get rid of those square roots? What did you have to do? Multiply by 5, some word that you've forgotten. Good. We'll relearn that word. Do you remember what it would be? It is the conjugate. That's the English word. I have no idea. Let's just say conjugate with a French accent. I'm sure you're fine. Do you remember what it looked like? You remember the words? Square root 3 and square root 5, but this time a minus. Because it made a difference of squares. Remember, you can, like, if you have x squared minus 9, that's factors to x plus 3, x minus 3. We call the x plus 3 and the x minus 3 conjugates. We call the x squared minus 9 a difference of squares because there's a difference in between. And x squared is a square, and 9 is 3 times 3, it's a square. So if you multiplied the bottom by that, you have to multiply the top by that. And what it did, well, the top you just have to distribute. But the bottom, because it made this difference of squares, it would be the first one squared, and root 3 times root 3 is just 3. Minus, because it's a difference of squares, root 5 times root 5 would just be 5. And all of a sudden, we don't have a square root on the bottom. We have square roots on the top. And your head says, what was the point of that? Like, I guess the point of it, historically, is that if you didn't have a calculator and needed to figure this out to 5 decimal places, this one might take you 6 hours. Whereas this one would take you 25 hours. So you would like the 6-hour method better than the 25-hour method. Now we have calculators. They both take the same amount of time to type into your calculator, push enter, and get the answer. So the idea of rationalizing the denominator for any practical purpose seemed like it was kind of useless in grade 11. However, it becomes very important in our calculus because now if I multiply by the conjugate here, which seems really weird, it's the same thing just with the plus sign in between. The bottom I'm going to leave factored out, but the top now makes a difference of squares. Differences of squares, super helpful and super important in calculus. And sometimes you make up weird ones like this. If I multiply out the top, I just get the x plus h, because it gets squared, minus the square root of x squared just becomes x. And now my x and my minus x cancel out, leaving you with just an h on the top, and there was just an h on the bottom. Those would go away. And we're left with this, which at this moment doesn't seem any nicer than what we started with. But for the purposes of calculus, will be beautiful later on. Interesting. So sometimes we make up weird things to simplify. They do come back and help us. And that idea of rationalizing the denominator is going to help us a lot in calculus. But for this one, I would have expected you only to get to the black part. There was no reason to change it to the blue one, but we'll see that reason later. And may as well introduce it already so you see it more than once. Okay. One more topic for today. Implicit and explicit forms of functions. We generally deal with explicit functions, especially if you have a graphing calculator. You can only type in things into your calculator if the y is by itself. Y equals 3x plus 1. If it's any other way, you'd have to rearrange it first. Any of those other ways are implicit forms. So here, I have 5x squared minus 6y equals 5. This is the implicit form because the y isn't by itself. I could rearrange this by getting the y all by itself on one side, then dividing everything by a negative 6, and then I would have an explicit form. This, you could type into your graphing calculator. What shape would it be? Parabola. It would be like that U-shaped thing. Graphing calculators, our graphing calculators, only deal with explicit equations. On your exam, you'll have your graphing calculator. It's probably the thing you'll use the most. On your exam, they've designed it to give you access to Desmos on the internet as well, which is really cool. You don't get the whole internet, right? It's not like AP exam with ChatGPT. No. You don't get AI or anything else, but they do give you access to Desmos. So it might be a thing that you want to also download on your phone for working at home or on your computer. I'm going to just show you maybe how it works. Here we go, Desmos. And Desmos, you can type in, here I'm going to look at that. I could type in 5x. And you're like, how do I do the squared button? You could click on that. Or you can use like, you know the little, this shape thing? Does anyone know the name of that thing? I often just call it little hat button. But I don't know.
The power button?
It's a power button for math. Is that what it's called? Doesn't it have French, like sometimes they put the hats on letters, make them sound funny? Okay, you can do that as well. So I could type in minus 6y. This is cool about Desmos is you don't need the implicit form. You could get your parabola just by typing it that way. What's also really nice about Desmos is like, oh, these are points you probably want to find. You can just click on them and they tell you the answer. rather than the long-winded graphing calculator method. So for some things on your exam, you might really like Desmos. There'll be other things on your exam you'll really like your graphing calculator because you'll know how to do it better. And on all our tests, we don't have that Desmos option, so you still need to know your graphing calculator for all your tests this year. But this is really cool. So if you've never played with Desmos, download it on your computer. Download it. There's an app for your phone. You can do some very cool stuff on there. Okay, well, that's not the right button. Here we go. This one too, if you wanted the explicit form to get the y all by itself, first of all, I'd have to get the square root by itself. And then I'd have to square both sides to get rid of the square root. And then finally, I could get y by itself. And y is equal to x squared plus 14x plus 45. It's a parabola. I'm kind of curious. If I go to my Desmos and I type in my original equation like it was, so I can hit the square root button. It was the square root of y plus 4 minus x equals 7. I get a parabola. What's weird about a parabola? Anything weird about that parabola?
It's only half.
It's only half of it. So the explicit equation is not quite right in this situation. Because it's only half of the parabola. What possibly could be the reason that they didn't want the other half? Square roots give you problems sometimes, right? You try to square root a negative, it could give you a problem. And in fact, algebraically here, this is kind of, I don't know, I think this is kind of cool. Sometimes you do algebra and you don't realize you screw things up a little bit. Like technically by squaring this, I give a possibility for some wrong answers. Right? Because this, if this is negative to begin with, and is x plus 7 ever negative? Sure. Negative 9 definitely wouldn't work. And square roots are always positive. When you square root both sides, you remember you have to add that plus or minus? How many of you have lost a mark on a quiz or a test at some time in your life because you did not do the plus or minus? Okay? For those of you that didn't raise your hand, you forgot. I'm sure you've done it at least. Or you like, no, I lost the marks before that. I never got that far. But you will forget that plus or minus when you square root both sides. Probably even this year, some of you will do that again. But that's why when I graph it in the calculator, it doesn't show up. And then there are some equations that you cannot, like this one, get y by itself. Ooh. How would you get the y out of the sign? And also out of this sign, and also out of that 2, all at the same time? Oh my goodness. There are some equations where it's actually impossible mathematically to get the explicit equation. But we can get an idea from calculus what it's supposed to be like, but we can't ever find out what it actually is like. This, I think, would be, oh, sorry, I'm really curious. What the heck would that graph look like? Sine xy equals xy. Wow, that looks fun. Xy plus cos x. Whoa! Minus sine y. Yeah, that's, you know what? I think that's what I had in my mind too when I saw that equation, right? That's exactly what I thought it would look like. Is it a function? No. I'm missing something? Oh, I'm missing the, oh, yeah. Well, I'm sure it'll turn out much nicer if I add that. I'm missing the negative 2y, which is supposed to be here. Not that it matters where I put it, but. Oh,
So much better.
so much better. That's how I was feeling this morning. Yeah, okay. Will you be asked to graph things like this? Absolutely not. But that is interesting. Desmos can do that. Your graphing calculator cannot. So something interesting about Desmos there. All right. Domain and range. A little review on this. I know I got off topic, so I always find out from Mr. LaFrance first thing in the morning. So how far did you get? And he's like, oh, I was like, when he told me, I was like, oh, that's not very far. So then I got off topic, and I'm like, oh, okay. So he ended with this part, so we're going to be perfectly at the same place. Set notation is when we write it. Oh no, that's interval notation. I'll put a big I beside this. And this is set notation. Sometimes in set notation, it is okay to just write what I have in the green circle. X is bigger than or equal to 0. Formally, you would have more stuff. You have like a squiggly bracket, and you're saying what you're talking about, X. You put a straight line. That straight line means such that. Whoa. Whoa. We're looking for X values such that X is bigger than or equal to 0. End of squiggly bracket. But probably in grade 12 you didn't have all those formalities, you just had the part in the green circle, which would have been fine. But if you have multiple choice questions and they add all the extra formalities, you get scared. So we show you all of them just so that you're not scared when you see them. Same thing with the range. You could go negative infinity to infinity, or again, this is probably all you wrote, right, when you wrote range. Y is an element of the real numbers. But if you add all the extra little squigglies, and such that. Well, I've got 1 minute to show you domain and range of the next two. Think we'll be able to do it for the bell? Yeah. Is everybody good here? Here, the domain, the solid circle means that's included. English notation here. Oh my goodness, right? We have a round bracket at the 5 instead of the backwards square bracket. And in set notation. Sometimes I call interval notation like the English way, and set notation like the French way. Because like French words, you start saying them and then like the end of the word, you just like don't say a whole end of the word. You have all this extra letters that you don't need. Oh, we didn't get finished. I'll show you the answers for the other one at the start of tomorrow.